Everyone, welcome back to Math 256. This is Scott. Let's get started. So what we are now going to be looking at is section 2.2, in which we will be exploring the geometry of systems as promised. So last time in 2.1 we got a little taster of the geometry of these systems of differential equations, and now we're going to actually delve into it. All right. So first off, I want to specify the terrain here, what we are going to be looking at. So the setup. The systems of differential equations that we're going to be looking at in this section are going to all be autonomous. So an autonomous system of first order ODEs, and in particular, we're going to have two variables in our system. Now, first, what does this mean? It means pretty much the same thing that it would mean for just a single differential equation. So, i.e., a system of the form dx dt equals and dy dt equals, and in both of these cases, we do not see a t on the right side. So these don't involve t. And to see why we need this situation, so do close my parentheses. I'll just eliminate my parentheses. Okay, and to see why we need this to be the case, just think for a second about what the direction field would look like if the right sides of these equations depended on t. Essentially, they would be constantly in flux, which is, a possibility, but it's not something that we can represent in a consistent way. All right, so then the goal here is going to be to understand the phase portrait, which is, in other words, the y versus x. The y versus x plane. And we're going to try to understand this in terms of the differential equation and what it has to say. Okay. So first off, some observations. First, just thinking about what these actually represent, it is literally the change in x with respect to time and the change in y with respect to time. So if the x is not changing, then what we would be getting is a sequence, or would be finding a point on which there was no horizontal movement. So note, where dx dt equals 0, there is no horizontal movement. And by the exact same token, and likewise, no vertical movement where dy dt equals 0. And if you're ever at a point where both are equal to 0, any point where both dx dt and dy dt are 0, will be an equilibrium. All right. Well, based on this, we can get our first glimpse of how we would go about trying to understand the geometry of this. We can start by isolating the dx dt equaling 0 scenario, and then the dy dt equaling 0 scenario, and see what each of those would mean. So so let's just define here Noclines. So Noclines, these represent the curves that we get when we set alternately the dx dt equal to 0 and the dy dt equal to 0. So the x nocline, or the x noclines, this is a curve that is produced by setting dx dt equal to 0. And then y nocline would be very analogous. So the y nocline would be what you get when you set dy dt equal to 0. So as an example, just something to get us started here. If we had x prime is equal to x plus y, and y prime is equal to negative 2x plus y, then the x noclines, or in this case just nocline, would come from x plus y equals 0, which then would just mean the line y equals negative x. So the curve here would just be the linear function y equals negative x, and then the y nocline would be from setting negative 2x plus y equal to 0, which then if we solve for y, just because when we can, that will usually be the easiest to produce version of the curve, then we would get y equals 2x. Now, the significance of these noclines is going to be in a couple of different avenues. So we can sketch the noclines on the xy plane, and then what that's going to help us do is it's going to help us to figure out the orientation of the curves that we would draw. For the x, nocline, uh, cover the curve in little vertical marks. I'll show you what I mean. To represent the fact that any solution curve that passes through the nocline must be vertical at the point of intersection. So here, just down a little bit further, we'll actually start putting this into practice. All right, so y equals negative x. So that represents just the diagonal line that goes down with a slope of 1. This is the x nocline, and what I mean by the vertical marks is just like this. Just put little vertical hash marks on there to indicate that if we were in the business of drawing any solution curves, the point where they cross this line, those solution curves must have all of their movement in the vertical direction. And then for the y nocline, do the same thing but horizontal. So put horizontal marks. So the y nocline here, so this was y equals negative x. This does not represent a solution curve. This represents actually more like it's more similar to a topographical feature on the graph, like if you were looking at a map. Okay, and then for the y equals 2x, that's one that's going like this. And we would mark that by horizontal tick marks. Now, what is the significance of the intersection of these points? Well, at the intersection of those points, it is neither changing in the x direction nor the y direction. In other words, it has an equilibrium. So the points where x noclines intersect y noclines are equilibria. So those are the equilibrium points for this system. Any solution that starts there will remain there. After that, who knows where it might go. So if it starts somewhere outside of that, it will be going in one direction or another. All right. Now, for each of the sections that are kind of marked off by these Noclines. So here we can see there are 4 regions to our curve. What we can do is figure out whether the dy and the dx are positive or negative, and we can use that to help us to orient the direction that a curve would be having while it was going while it was traversing these sections. So so the Noclines will let's say divide the phase plane, also known as the xy axis. Phase plane, phase portrait. We'll divide the phase plane into regions. For each region, we can determine whether dx dt and dy dt are positive or negative. And then once we have determined that, that will tell us the direction that a solution curve or a trajectory would move while it was in that region. This indicates the direction of motion of solution curves through that region, or in that region. Maybe doesn't leave that region, in fact. It's very possible. So here for our example, let's just go back over here and we'll just ask ourselves in each of these sections what are we going to get. So this point right down here is clearly 0, 0. That's the equilibrium. So just mark that off to the side. Equilibrium at 0, 0. Now over in this region, one way we can determine the direction of motion is literally just plug in a point. So let's just say at, and we can just pick whatever point seems convenient for us, and we could just say at 0, or sorry, at 1, 0. 1, 0. So that would be over here somewhere. So at 1, 0, so that's x equals 1, y equals 0. X prime equals 1, y prime equals negative 2. So that means that we are going positive in the x direction and negative in the y direction. And so that means we are talking about a curve that's going like that. So it's going down. Good to know. So I'll just label these A, B. So let's just say we want up here. Let's just say that, or actually, better yet, let's just go ahead and keep it nice and consistent here, B. So B. So at 0, 1, x prime is going to equal 1 again. Y prime is going to equal 1. So that means we are going up and to the right. And then here, let's say we want a point over here for C, and you just take the points that are most convenient. So for C, so that would be at negative 1, 0. Well then, what do we have? So x equals negative 1, y equals 0, so that means x prime would equal negative 1, y prime would equal positive 2. So that means we're going left and up. And then for D, that is going to be that's going to be something in this region, for example, 0, negative 1. X prime is equal to negative 1. Y prime is equal to negative 1. And so we are talking about something that is going down and to the left. All right, so we can see here that what we've got is, it looks like we've got a generally clockwise motion going around on all of these points. And we can see also that they do seem to all be spiraling out from the origin. None of them are pointing towards the origin. So then what that means is, so here we can, based on this analysis, we can figure out at the actual Noclines whether to indicate upward, downward, leftward, rightward direction based on our representative points. So then we can put arrows on the marks on our Noclines to indicate the direction a curve would cross it. And so if we go back to the one we're making here, so we want to indicate the direction a curve would cross it. Here, they all have to be going vertically when they're crossing this Nocline. And from what we're seeing on the motion in this whole half of the quadrant, or of the xy plane, always going to have to be up, 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 up on this side. And on this side, we can see it's going to have to be down, 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 down. Similarly over here, because we've got this clockwise motion, we can see it'd be having to go through this one, to the left, to the left, to the left, and this one to the right. And then from this, what we could do is if we wanted to try to just generally sketch a solution curve, we could take some initial condition and just see what that would kind of indicate. So if I wanted to go out, it would be maybe going somewhere like this, and then maybe down like this, etc. So and then it'd probably be like a spiraling outward type of curve. However, these kinds of things are a little tricky sometimes to try to figure out by hand, but we can but that would be our hypothesis, our speculation. So then so then based on this, we can try to we can try to uh, try to figure out what would be going on the with solution curves. So then try sketching some representative solution curves. All right. So this would be what we would sort of generally be expecting from solution curves here. It looks like it's spiraling generally outward. Now, who knows? Who knows? Who's to say what the actual situation is like for these? Well, that's where technology can come in and help us to resolve these things. So let's switch over and take a look at what Bluffton, for example, would show us for this very same situation. All right, so here we are at our typical starting position. We have put Bluffton differential equations into the search bar of a search engine, and here we go. Let's see what Bluffton can offer us. So here we see our typical Bluffton stuff, and we'll switch over to system. All right, so now we will enter our system. The first equation already matches. Now we'll just put the second one in. Negative 2x plus y, and hit enter. You always have to hit enter after you make any change on a Bluffton line, otherwise it won't register. And now get rid of this curve, which is not really relevant for us. And let's actually see how this looks compared with what we were looking at. So if we wanted to actually plot our Noclines on here, we can using the little bar down here. We can put y equals negative x. That was one of them. And so that red one will represent our x Nocline, and then y equals 2x. That will represent our y Nocline, and it's green, but let's make it blue so it's a little more different. And if we look at the x one, it's a little hard to tell because we don't necessarily have any segments that exactly go through it. There, that's a little bit better. But everywhere where one of the vectors does intersect this red line, it is vertical at that point. And everywhere where the arrows intersect the blue line, it is horizontal at that point. And you'll notice that there is this generally clockwise swirling motion. Now, based on just our guess, we speculated that a solution curve would be spiraling outward, like basically this, and sure enough, it did. And then we also tried to see where the one here would end up, and we get it going up in that way. And you'll see that this actually fits pretty well with what we were able to tell just from an exploration of the x's and the y's and whether they were positive, negative at each of the points, and then based on the Nocline, the Noclines were able to break the phase plane up into regions that we were then each able to analyze. So you can see that this analysis produced a very good representation of the behavior that these solutions would be having. Now, these are the solution curves. These are the trajectories that represent y versus x. However, x and y are each functions of t. And so if you want to see them as their curves in terms of the t, you can go down to this option down here, the numerical solution tables and time plots. And what that will actually do is it will actually give you then a curve for each of the x and y values that then we can use to track their behavior. Unfortunately, so Bluffton has a lot of virtues. One of its virtues is not on the graphing side of things. It does not really uncouple the graphs from whatever their original scale was. When you do the zoom in and zoom out, it only changes the x scale, and so unfortunately, you end up losing a lot of the curve this way. However, if you give a wider spread on the values for y and on the actual slope field, and I believe that when you do this, no, never mind. So yeah, so the vertical axis of this is kind of tied in with whatever it starts off being, and then after that, it's a little bit inflexible. So that's an unfortunate part about Bluffton. One of the nice parts about Bluffton, though, is how easy it is. So now let's take a look over at Sage and see what it has to offer. All right, here I just brought up chapter 2 from your textbook, and we can look at the little Sage scripts that it provides. So if you go to 2.1 and you scroll all the way down to the bottom, you can see here what we've got are some different scripts to accomplish different things, and they're all based on this system of equations right here. So let's just try to modify this to match our system of equations. So the first equation, so the way the format of this is that you define this f to be essentially the f prime component, and then you define the y, or what? Sorry, my thing just clicked on something weird. Okay, so you define the y to be the y prime to be the second component here. So for our example, it'll be what is it? It's negative 2x plus y. And now let's have a look. So this is first going to generate a direction field, and Sage is a little bit particular about how you enter things. One great difference between it and Bluffton is that it is a lot more persnickety about these types of things. Now, the first script here gives you a direction field where all of the vectors are actually scaled by their magnitude, or sorry, where they're actually their length. The length of each vector is actually untampered with. It just fits its magnitude. Now, that is not usually the way we look at our direction fields. And so what this next script does is it actually, let me just take this, copy this, this F so I can use it for all the other ones. What this next script does is it normalizes all of the vectors by turning them into unit vectors. So evaluate that. And so now all of the arrows are the same length. So that's generally the way we like to do these because they are otherwise a little bit too messy. And just looking at what we have here, so it's plotting it as a vector field. This is giving the X range and the Y range. So let's say I wanted my Ys to go from -10 to 10. This is where I would make that change. So this is getting the direction fields, and this next one takes us one step further and adds axis labels to the plot, which is not something that's a huge priority for us. But if we can include them, we might as well include them. So see now this says X along the X one and Y along the Y direction. Nice. Now, if we want to actually get the solutions of these, then we can get the Runge-Kutta solution to this system, which is something something that, where did I paste that last one? I don't know. Oh, here it was. Okay. So Runge-Kutta we discussed for just a single differential equation, but here you can also do a similar thing for a system, as we'll discuss actually in the very next section. But there would be the actual values for the X and the Y for all of those. And then we can, so that's all well and good, but we would rather actually probably look at it. So here we can get the time plots. Take a second because it's got a lot of data points in there. So these are the time plots. These represent the time plots for the two functions, and that's all well and good, except we don't really know which one is which. So this last one here gives you, or this next one here gives you some more labels and such, and let's see what it gives us. So here now we have the X and the Y given to us in this particular one. Oops, forgot to change this. Forgot to change this one to our new equation. That's why it doesn't look like it did on Bluffton, but here we go. Okay, so there it is, looking like it did on Bluffton. And here now the scaling. So the scaling is a little bit more convenient, or at least more flexible. The downside of this whole thing is that we essentially, so it basically sets the scale automatically, so that includes all of the data values on the table. The downside of this whole thing, though, is that we're kind of stuck with this ungainly syntax. So here we've got initial conditions, we've got the independent variable, we've got the end point, we've got the step size, and so we're kind of bound to just sort through the forest of these various components in order to find the place to make the modification that we want to make. But on the plus side, we can see the whole graph as desired. And then if we want to actually plot the curve in the, so we want to plot the curve on the phase plane. So in other words, with the X and the Y as the two components, then you can make that change here. And what we've got is this, which now just graphs Y versus X. And if you want to pretty it up, you can by doing this, by using this script, which gives you adjustments for font size, thickness, and all kinds of things. Let's have a look. So there it is. It's even got a little arrow, although the arrow is a little bit misleading here. So this is not a very helpful arrow, but its heart is in the right place. The problem with the arrow is it's too close in here, so we can't really see which direction it's supposed to be pointing. It's basically the initial condition, and it's pointing us up that way. But in any case, and we can change the thickness. You can make it 2, for example, which would make it less thick than it was. You can make it thicker. You can make the graph smaller by changing the end point. There we go. Now you can make better sense out of the arrow. Got the little spiral that we know. Let's see here. We can now add a vector field to it. But let's see. So our vector field is all clustered right around here. It's not very good looking. So let's change this, make it a little bit smaller. Oops. Change the endpoint to 5. Still not so great. And so let's see here. Oh, it's because our vector field isn't going out as far as our X and Y values are, it looks like. So we want the X to go, looks like, I don't know, -10 would be enough. And we'll make the Y go out to, out to the 80. And then the Y, so this might be a big disaster here. The Y lower value, -250. And then positive, looks like about 50. So there we go. So there's the vector field along with the graph, so that the vector field is actually made to fit in the same space as the graph. And this is how you can make the modifications that you want to make to the Sage scripts as provided in order to produce the graphs that you want. There it is. Okay, so that's what it looks like on the technology side. Bluffton, the pros are that it's super easy, but you can only do what it can do. For Sage, the pro is that you can do a whole lot of things. The con is you got to learn how they want you to do it. So that's just an interesting little trade-off there that is not uncommon when it comes to sophisticated solving software. All right, so let's see, back to notes. All right, so let's try to work out another example of a similar nature. This one is going to be from ecology, and it's going to be a competing species model. So here, we'll have the system dx dt equals x times 1 minus x, and then minus beta x y, and then we'll have dy dt equal y times 1 minus y minus beta xy. And what the meaning of this is, so x and y each represent a certain species. They are competing for resources in a certain habitat. And the first part of each of these represents essentially the what would happen to one of the species if the other one were completely absent. And this actually would represent a logistic population model with a carrying capacity of 1. So let's say 1,000 individuals, 1 million individuals, something like that. In other words, it's basically scaled according to its carrying capacity. And the same thing down here. If there were no individuals of species Y, X would just be a logistic population, and likewise for Y. Then what these two terms over here represent are the effect of the interaction between the two species, and the higher the value of beta, the more strongly the species interact. So let's just say beta equals 1/2. Or actually, sorry, say beta equals 1/3. So this represents a situation where the two species interact weakly, not that strongly. All right, so in other words, dx dt is in reality x times 1 minus x minus 1/3 xy, and dy dt is going to be y times 1 minus y minus 1/3 xy. All right, so be it. Now let's just go through the process that we outlined above. So part A, let's just say find the Noclines. All right, so now it's a little bit more complicated as far as the equations that we're looking at, but the process is still the same. So the process for finding the Noclines is we'll just take the dx dt and set it equal to 0. But what's dx dt? That's x times 1 minus x minus 1/3 xy is equal to 0. So these are the x Noclines. And then if we if we manipulate this a little bit, we would get, for example, x times 1 minus x equals 1/3 xy. Now, one obvious way that this equation could be true is if x equals 0. So the x Noclines, one of them is just going to be at the curve that is represented by x equals 0. And then as for the other one, if x is not equal to 0, then I can divide both sides by x, multiply both sides by 3, and then that would be y equals 3 times 1 minus x. So in other words, y equals negative 3x plus 3. So okay, we've got a straight line that has this slope and this y-intercept, and we've got a vertical line at x equals 0. Now let's do the same thing, but for y. So the y Noclines. So those come from setting dy dt equal to 0, which in this case would be y times 1 minus y minus 1/3 xy equals 0, which we can then rearrange in the same way. So y times 1 minus y is equal to 1/3 xy, which then gives us the same kinds of solutions. So we have for our y Noclines, we have the one solution where y is just set equal to 0, and then left side equals right side for sure. And then if y is not equal to 0, then we can divide both sides by it and multiply both sides by 3, and that gives us x equals 3 times 1 minus y, or actually, so since I most likely want to solve this for the y, I'll actually, I shouldn't have multiplied both sides by 3, so I will divide both sides by 3, and now I will add y, subtract x minus 3 from both sides, and get y equals 1 minus x over 3, and so that'll be the other one. Okay, so those are all of our Noclines. All right, so be it. Now I'm just going to call this one Nocline 1, Nocline 2, Nocline 3, and Nocline 4. And now for part B, let's find the equilibrium values, or the equilibrium points. All right. Well, remember what makes an equilibrium point? It's when an x Nocline crosses a y Nocline. In other words, the derivative with respect to x and the derivative with respect to y are both equal to 0. And so let's just say 1 to 3. So then that means we've got the point x equals 0, y equals 0. So in other words, 0, 0. All right, 1 to 4. So where 1 crosses 3, where 1 crosses 4. So then we've got x equals 0, y equals 1 minus x over 3. And now if we substitute the 0 into here, we get y equals 1 minus 0. And so that equals just 1. And so that gives us the point 0, 1. Now we'll match up Nocline number 2 from x with Nocline 3. So that gives us y equals negative 3x plus 3 and y equals 0. So then that means that 0 equals negative 3x plus 3, which means then that x equals 1. And so then this gives us the point of 1 comma 0. And now finally Nocline 2 matched with Nocline 4. So that's again y equals negative 3x plus 3 and y equals 1 minus x over 3. And if I want to solve this system of equations, now it has become a system of just regular equations, not a system of differential equations. I can just set them equal to each other. Negative 3x plus 3 equals 1 minus x over 3. And then let's say I multiply both sides by 3. And so I would get negative 9x plus 9 equals 3 minus x. And if I add x to both, or actually I'll add 9x to both sides and subtract 3, I get 6 equals 8x. And then that means that x equals 3/4. And then that means that in turn, y equals negative 3 times 3/4 plus 3, which is equal to, let's see, negative 9/4 plus 3. So that's negative 9/4 plus 12/4 is equal to positive 3/4. And then as a quick check, does that line up over here? That would be 3/4 divided by 3 is 1/4. 1 minus 1/4. Sure enough, it is 3/4. Okay, so that gives us the other equilibrium point of 3/4, 3/4. Okay, so now we have the equilibrium points. So now let's try to use the information that we've got to actually sketch what we can of the phase plane. So C sketch the phase plane. All right, well, if these are two species of animals, we don't have to worry about negative values of x and y. So we can actually just confine ourselves to 0. And we'll put in the values that are of note here. So one good way to get this started is to start by just plotting the equilibrium points, and then use those to help you sketch the Noclines. So the equilibrium points would be 0, 0, 0, 1, 1, 0, and then 1/3, 1/3, and then maybe up a little bit higher than that, and then the Noclines here. So let's see. Let's take the one. This is x equals 0. So this is an x Nocline, which means that the tick marks that we're drawing on it are all vertical, which make them a little hard to see, but there they are. And then y equals negative 3x plus 3. So that one is going to be a line. A line that goes over here. Negative 3x plus 3. So it's the other. So it's the other x Nocline. So the reason why why I was stopping for a second there was I was thinking, uh-oh, is that supposed to be another equilibrium? But remember, the equilibria come not when the x Noclines cross each other, but when they cross the y Noclines. So that's the difference here. Okay, so there's the y equals negative 3x plus 3. All right, and then we have the other one at y equals 0, and sorry, this one was a vertical, or deserved vertical tick marks, just because it is an x Nocline. All right, y equals 0. That's a y Nocline, so it goes this way. Sorry, again, the reason I hesitated there for a moment was because I thought something was possibly going wrong here, but no, the thing that was wrong was I accidentally marked a point there that has no real relevance. 3/4 was supposed to be my other one. That was more like 1/3. I was looking at the wrong thing there when I was thinking about that. So let's just let this line speak for itself, and then wherever it crosses the other Nocline, that's where we will find our equilibrium. Okay, so that was 3/4. This is the y equals 1 minus x over 3, so it's a slope of 1/3 and a y-intercept of 1. And this is again a y Nocline, so that means it's going this way, this way, this way, this way, this way, this way, this way. These are all supposed to be horizontal. To the extent that they're not, it's just because I'm writing at a somewhat slanted angle, but they're all supposed to be horizontal. Okay, so now let's just call these points here, 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 and here. So these are the regions that we are interested in. Technically speaking, there are actually a couple more regions outside of here, but those are not of relevance to us. So we'll just call these the four regions, and we'll just say A, B, C, and D to name them. All right. Region, let's say A to start with. So we just need a representative point, and if we look at it, so the point that is maybe so something smaller than 3/4 but bigger than 1, like let's say, so let's just say 1/4, 1/4 would appear to be in there. So just as a quick check, if I put 1/4 in here, are we going to still be below this line? So 1/4, that would make it negative 3/4 plus 3. So that will, so this line will still be taller than it. So, yep. Okay, so I can just go with 1/4, 1/4, 2, for example. So then, what are we going to get? We're going to get x prime equals, and So x prime equals something, y prime equals something else, and here you can just basically plug the numbers into a calculator, or you can use something fancier if you want to evaluate it. I just happen to have this handy, so I'll use it. So okay, so if I want the x prime, that's going to be 0.25 times 1 minus 0.25 minus 1/3 times 0.25 times 2. It's just again what I happen to have handy, so I just entered in the x prime thing as given. So that's equal to 0.02. So in other words, positive, although not very. Positive, but not very. Close to 0, which makes sense because I'm close to that line where and in fact I'm sandwiched between these two lines where the x derivative is 0. All right, so then for the y prime, I can just do the same thing but with the y values. 2, 1 minus 2 minus 1/3, and that term is actually the same. And I get negative 2.16. This is positive, this is negative, and based on that, we are talking about something that is going pretty steeply down that way. Barely positive on the x, and highly positive on, or highly negative on the y. So based on that, I'm going to speculate that these are going down. And then for B, I just need a point representative of that, and let's just say 1, 1. 1, 1, for example. So then x prime is going to equal 1 times 1 minus x, which is going to be 0, minus 1/3, so negative 1/3. Y prime is equal to, so y prime is going to equal, so in this case, what we're going to have is the same thing. So it's going to be negative and negative, which means we are, and they're equally negative in both directions. Here, once again, I want it to be slightly positive on the x, but highly negative on the y. Basically vertical, but going ever so slightly to the right. Here we are, so in this one, we're talking about something that is going down that way, which matches these arrows. Now for C, we could take 0.5, 0.5. So just a representative point from C. And then that gives us, so that's again just a representative. So then x prime will be, so it's going to be 0.5 times 1 minus 0.5. So that's going to be, 0.25 minus 1/3, 0.5 times 0.5. So it sounds like it's going to be positive, but I guess I need to actually calculate it. So it is indeed positive. And y prime will be the same, because the calculation will be the same. So in the case of C, we have an arrow going up that way. And then for D, for D, we can pick a point. Just gotta make sure that we stay below this line. So if we pick a point like 2, and then as long as it's a number that is below 1/3, so 2, and then 1/4. So just to keep things kind of symmetrical with that one. Then, actually, because of the symmetry of this, I can tell that this is going to be the same as what the y was before, and the y is going to be the same as what the x was before. And so that means we have a negative and a slight positive for these. So that means we are talking about something that is going generally, mostly, this is going mostly to the left and ever so slightly up. Okay, well then based on this, we can see how to fill in these arrows. And because it's going slightly up from both directions here, we can see that it's going to be, well, actually, so here we just end up, it looks like up and down and down, and left and left. And over here, looks like slightly right, slightly right. And essentially what we get is that it looks like the solution curves here will basically go something like this. So they seem to be essentially converging on this equilibrium here, 3/4, 3/4. So whatever way they happen to be going here, that's where they'll end up. So that appears to be where the solutions are tending. Now let's put ourselves in the position of one of these solution curves. Let's just say D. So let's just say for D we wanted to use the initial conditions x of 0 equals, let's just say it equals 3 y of 0 equals 1. What happens to x and y as t goes to infinity? So that would be the question we could ask, and we will just kind of plot it out. So we think about it here. If we start out here, we know that the behavior of it is going to be going in and in and in, and whichever way it goes, there's only one ultimate destination here, and that is 3/4, 3/4. So it looks like in both cases we are converging on the point 3/4 and 3/4. So this equilibrium, because of this, is called a stable equilibrium. It's also called a sink or an attractor for the same reasons as we saw before. But we won't get into the exact classification of these until we have learned a little bit more about the algebra behind them. But for now, let's just now switch back over to Bluffton and see if we can confirm our findings. All right, here we are back at our home base, which is just Google search results for Bluffton differential equations. And from here, we can get to whatever we need to get to. So just go to system, because that's what we're talking about here. Get rid of the curve that was already on there so it doesn't distract us. And we'll put in the differential equation that we've been dealing with here. And if you're not careful, you can sometimes get into some formatting trouble with Bluffton here. Let me show you. So if you just do this, x and then parentheses, the Bluffton thinks that this is treating x like a function, like the parentheses here are function notation. So make sure you're liberal with with multiplication symbols. Also, if you do x, y, again, Bluffton is going to just think that this is defining a new variable called x, y. So make sure you put lots of asterisks for multiplication. That's one thing where Bluffton is a bit inflexible on its notation. And here, same thing, but with y. And then what we will look at is a reduced window, because we don't want we don't need all four quadrants here. If we're talking about species of animals, then this can be 0 for the minimum x. This can be 0 for the minimum y. And now if we look at what we see here, it's interesting looking, but let's put in our Noclines as well. All right, so I'm gonna make my x Noclines all red, I think. So so you can type in just x equals 0. If you so you can enter in a couple formats. These you can do. You can put in just the function. You can put in something that is polar, parametric, or as in this case, you can put it in as an implicit equation. Okay, so there's the red one, and actually just to enable us to be able to see it a little bit better, I'm gonna actually give us a little bit. I'm gonna give us a little bit on the negative side, 0.5, just so we can actually see the Noclines. Okay, now for the next one. Here, I'll put in the y equals negative 3x plus 3. And I will change its color so that all my x Noclines are red. Okay. Now here, like this line, at first it doesn't look like it has much to do with these, but if you look at it very carefully, everywhere an arrow is crossing it, that arrow is vertical. Now, sometimes that arrow is going up, sometimes that arrow is going down. That all depends on where we are in the grand scheme of things. But all of the arrows crossing it are vertical. That's what it means to be an x Nocline. Okay, now for the y Noclines, we have y equals 0. That was one of them. And blue is a good color. And then for the next one, here, I just want to use y equals 1 minus x over 3. And again, I just want to keep them all the same color so that it can help me see what's going on here. Okay, so once again, if we look through this, it looks like every place the arrows cross this particular Nocline, they are horizontal. That may not appear to be the case on this one, But if we were to increase the resolution a bit, well, it still doesn't appear very, very clearly. Some of these ones that are where the rate of change is rather drastic, you sometimes don't get to see. You don't get to see exactly what's happening because it's already changed by the time we get there. But in any case, now let's say we want to take the initial conditions where the initial x value is 3 and the initial y value is 1, and we submit that. Let's just see where it goes. So it looks like it's coming in hot, and it goes right on through the blue and in towards the equilibrium right there. And in fact, no matter where we start this, as long as we're in one of these sections over here, we are always headed towards that equilibrium. So this is just a fact about differential equations of this sort, that if we have competing species, but the competition is rather weak, as reflected by the fact that our beta value is rather small, then what we effectively will have is them converging on their equilibrium point. So their shared equilibrium point. So both of them are almost reaching their carrying capacity, is what's going on here. They're sharing the environment between them. Their interactions are weak enough that it's not going to push either species to extinction. Just as a point of comparison, by the way, let's clear all these and all these. If we change the equation a bit in order to make the interaction stronger, like instead of 1/3, if I made this equal to 3 and 3. So now the interactions between the species are quite strong. And there's still a place where the Noclines cross. I'm not going to go through the whole thing of finding the Noclines again. But if we start looking at the solution curves, if we look at what's happening, we essentially have one of two cases here. Either they approach the, and here, let me make this actually 2 and 2, just so we're zooming in a bit. So basically what's going to happen here, so we have strong interaction between the two species, and what happens is every solution essentially ends up in either at either 1 for species X or at 1 for species Y. So essentially these two species cannot coexist. If they, no matter what their initial configuration is, it ends up settling on either total domination by species X or total domination by species Y. They both end up at one of those values. So here, this curve represents total domination by species X and extinction of species Y. Whereas if we go back to the other one, it's the opposite situation. No matter how things start off, they always end up converging on the sort of shared scenario where they're both at 0.75. And if you look at the table of values, no matter what our initial conditions are, as long as we're in the first quadrant, the X and the Y values both are converging on 3/4. So that's what's going on with this. Again, this term represents interaction. This coefficient represents the strength of the interaction. And if we make it, for example, like 1, then we end up in the sort of boundary case where we end up with kind of weird things going on. And anything above 1 is going to be a case where where one species ultimately inevitably drives the other out of existence. So if it's 1.5 and 1.5, in this case, you can see every solution curve ends up at either 0, 1, or 1, 0, meaning domination by one species, extinction of the other. And anything below 1, ends up with the two species agreeing on some sort of a shared allocation of the resources, and they end up at the equilibrium that the math indicates. So here it's not quite as shared as it was on ours for some reason, but it is still a shared existence. And notice weird things happen if you put in negative values, but of course they would be weird because negative populations don't really make sense physically. Okay. Well, anyway, so that is a little bit of bluffed-in confirmation of what we were just talking about. And so on that note, now that we have been validated by technology, we can call it a section and move on with our lives to section 2.3. All right, well, till then, bye.